Hello everyone, welcome to my talk. My name is Wenling, and the title of my talk is A Lattice-Based, Key-Insulated, and Privacy-Preserving Signature Scheme with Publicly Derived Public Key. This is a joint work with Zhen, Khoa, Nguyen, Guomin, and Yu. This talk is made up of 4 parts. The first part is an introduction of Bitcoin-like cryptocurrency's privacy vulnerability in anonymity and the solution given by signature scheme with publicly derived public key. The second part introduces the lattice signature and trapdoor delegation, which are important building blocks in our scheme. In the third part, I would introduce the naive construction and the necessity of KeyPrivate PKE schemes. In the fourth part, we'll see our whole construction and the intuition of privacy preserving and a small conclusion. Introduction. In a Bitcoin-like cryptocurrency, a signature scheme is used to do the authentication work. The public key, or sometimes called the verification key, is viewed as the address. The belonging of any coin is recorded by its owner's address. To pay is to output a new coin with the payee's address and sign a transaction that consumes the old coin. Of course, everyone can check the legitimacy of the transaction by the address given by the old coin. To be able to be paid, a user announces its address to the public. This raises the problem that the payer and payee's identities are accessible to the public, and the belonging of coins are readable to the public, which causes severe problems if treated carelessly in a system. We now introduce a crypto primitive called PDPKS that solves this privacy vulnerability. PDPKS stands for Publicly Derived Public Key Signature. Generally speaking, it is a key derivation signature scheme, similar to identity or attribute-based signature scheme. A difference is that in PDPKS, a status of all participants are equal. In a PDPKS scheme, after setting up and the public parameters abbreviated to PP has been announced, each user generates and holds its master key pair and announces its master public key. Here, publicly derived public key means anyone who sees the master public key of Bob could derive the derived public key by itself without any interaction with Bob. And we say a DPK derived from MPK is linked to MPK. As you can see in the graph, the linkability is also checkable with the corresponding master private key. This allows Bob to check whether the address DSKB written in the coin by Alice is his. To derive the secret key of given DPK, MPK is also needed. By derive the corresponding DPK of DSK, the signing and checking procedures can be done with DPK and DSK, just like the signing and checking procedures done with signing and verification key in a digital signature scheme. If the derived keys and the signatures mix no information of the master key pairs, one can immediately see the anonymity of both sides in a transaction and the ownership of coins are protected. The correctness and security of PDPKS scheme can be naturally derived from such of signature scheme. In detail, the security of PDPKS scheme is defined similar to the EUFCMA of a digital signature. As you can see, only accesses of delegation and checking oracles are added. This ensures that the damage of a compromised derived secret key will not spread to any other derived secret keys. This strong security property protects the participant's account even if it carelessly leaks the private key of a small amount of coins. Eve wins the game if she can forge a valid key message signature triple, just as you can see in the slide. And we see the PDPKS game is security if any PPT adversary Eve can win a game with negligible probability. The privacy of a PDPKS game describes that given a DPK derived from some MPK, Eve can't even know which master public key the given DPK is linked to. In indistinguishable words, it is the DPKs of Alice and Bob are indistinguishable to Eve. To make the definition significant, we'll know if to ask for DSK derivations, checking and signing. In this sense, even if she the published coins or transactions, she would not know the owner of the coins or any side of the transactions. More specifically, the privacy can be defined as shown in a graph. Here, given two MPK generated by keygen algorithm and the derived public key derived from one of them, Eve has to guess the linkability of the DPK right to win the privacy game. And we say the game is privacy preserving if no PPT adversary can win the privacy game with non-negligible probability. In the process, Eve is given the accesses to the DPK derivation oracles, checking oracles, and the signing oracles. And of course, Eve cannot ask to check the linkability of the challenge DPK. This captures the fact that even given both the derived public key and signatures, no attacker can identify the master public key. PDPKS game was firstly proposed by the work done by Liu et al. They have proposed a parent-based PDPKS, which has the functionality and provable security. However, due to the hardness assumption is not quantumly hard, their scheme lacks quantum security. Considering the enthusiasm of the academia and cryptocurrency community of quantum security, we improved their work to construct the first quantumly secure PDPKS game. Part 2. Lattice signature and trapdoor delegation. Short integer solution problem is an average case lattice problem and is asked to find the short non-zero integer solution of given homogeneous equation system efficiently. It is assumed to be hard for polynomial beta and m with q larger than beta square root of n. Moreover, there's no quantum algorithm that solves this in these parameters efficiently. A cis-like problem called ICIS, where I stands for inhomogeneous, asks to give the non-zero short integer solution to inhomogeneous linear equation systems. It can be solved when given some extra information called trapdoor. As shown in a graph, the solution z prime of az equals u can be found when given the trapdoor Ta efficiently. Moreover, the work done by Alvin and Packard has shown an algorithm called trapgen that generates almost uniform A with trapdoor. And if we hash the message M with some randomness R to U, we could use TA to generate short non-zero Z prime as the signature. Notice that here, if we treat TA as the secret key and A as the public key, we obtain the digital signature scheme. This is the Lattice-based signature scheme given by Gentry et al. The Z-prime generated with this kind of trapdoor has some entropy. So, if we have the ability to forge the signature, we gain the ability to solve this by this equation A times Z minus B prime equals 0. Therefore, the hardness of this ensures the security of this signature scheme. To enable derivation, we resort to works done by Bowen et al. These works proposed an algorithm that delegates these instances to some other these instances with higher dimension, such that given A, B, R, and the trapdoor of B, the algorithm delegates the trapdoor of F equals to the concatenation of A and AR plus B. With suitable choices of the distribution of A and R, shown in this slide, we have F is statistically close to the uniform distribution. In this sense, F hides B and can be regarded as the TPK response scheme, and the delegated trapdoor TF of F is the DSK. We now give a naive construction of lattice-based PDPKS. Alice generates its master key with traction. She resorts to some lattice-based PKE scheme and generates the PKEK pair.
EPK-ESK. She sends B and EPK to Bob. For Bob, he has to choose A and R, but should not leak this to the public. So, instead of choosing A and R directly, he chooses a random T and encrypts it to tau. He hashes T and tau with some hash functions G1 and G2 to get A and R, and then makes a F. F together with tau is the derived public key and has been sent to Alice. After tau is received, Alice can decrypt it to T and recover A and R by G1 and G2. Thus, Alice could check and delegate the trapdoor for F, and we achieve the functionality of PDPKS scheme. Since tau is encrypted, it seems that the public could not figure out B by DPK. This is right, but that means the scheme is privacy preserving, and the reason is that tau itself might leak information about EPK, which also marks the identity of Alice. To fix this, we introduce key-privacy PKE scheme. 3. Quantumly secure key-private PKE scheme. The key privacy of PKE has been proposed by Belair et al. It mainly says that if could not figure out a given ciphertext is encrypted under which public key. Similar to plaintext indistinguishability, key privacy includes passive and adaptive key privacy. The difference is whether if is given the decryption oracles. To the best of our knowledge, there is no already exist construction of quantumly secure key-private PKE. But we notice that the LWE-based PKE scheme given by Regev is passive key-private. To achieve adaptive key privacy, we resort to Fujisaki-Okamoto transformation and prove that such transformation transforms a passive key-private PKE to an adaptive key-private one. Under such transformation, we could obtain a PKE scheme that is both IKCCA and indistinguishable CCA2, which is sufficient for our PDPKS construction. Part 4. Quantumly secure PDPKS construction. By substitute the PKE scheme with an adaptive key-private and CCA secure one, we can obtain a secure PDPKS scheme
as sure in a graph. Such Khoa scheme has been sure in a graph. Here, the PKE scheme can be constructed by LWE and FO transformation, and the parameters for Cs is sufficient for the LWE. Therefore, the security and privacy of the whole scheme can be based on the hardness of Cs and is potentially quantumly secure due to its quantum hardness. By this scheme, to pay a coin to Alice is to delegate a DPK of her and output the new coin marked with DPK, and then signs the transaction. And for Alice, she can check the legitimacy of the transaction by Bob's derived public key and check whether Bob has paid to her by checking whether the address in the new coin is linked to her master public key. When Alice wants to spend the coin from Bob, she can delegate a corresponding derived secret key and sign by it. The security of all scheme can be inherited from such scheme introduced by Gentry et al. Here, since the salt is added to the hash, there will be negligible probability that the hash results of two messages are the same. This shows that all scheme is safe under the privacy game, and its security is based on the Cs assumption. Due to the CCA2 security of PKE, the PPT adversary Eve could call the G1 and G2 autocalls with any T used by Bob with negligible probability. And without such calls, the matrices A and R seems uniformly random to her, and it would be unlikely for her to get the identity of Bob with such Fs. Since the PKE scheme is also adaptively KeyPrivate, Eve can't get the identity of Bob with the ciphertext tau. So, the privacy preservation is achieved together by the uniformity of F and the key indistinguishability of PKE. Since the CCA2 security and adaptive key privacy can be based on the LWE assumption, which has been implied by C's assumption appropriate parameters, our whole scheme is lattice-based and potentially secure against quantum's adversaries. We now make a small conclusion of our scheme. In a proof, G1, G2, as well as the hash function of messages are set to random autocalls. So, refer to our paper, one could check that our scheme has provable security and privacy preserved in RO. And due to the quantum hardness Cs assumption, our results provide a potentially quantumly secure PDPKS scheme that protects the privacy of participants in a Bitcoin-like cryptocurrency system, even under quantum attacks. However, due to the large parameter city in C signatures and trapdoor delegation, our scheme is not practical. We regard it as a stepping stone to the goal of practical and quantum-resistant privacy-preserving crypto primitive in Bitcoin-like cryptocurrencies. Okay, that's all of my talk. Thank you for your listening.